In this video, I'm going to talk about some general concepts about camera tracking, also known as match moving, and the related compositing techniques. As a result, it is not related to any specific software, nor is it intended to provide instructions on how to implement and practice these techniques. Essentially, this video is intended for those who have no experience with these topics and want to get a general idea of these techniques. The compositing of a green screen shot with other sources, such as real footage or 3D rendering, is an extremely useful application of match moving. Using a green screen, we can isolate our subject and then composite it with other video sources. Making a small-scale set, which we can also do at home, is the simplest and cheapest way to practice this type of compositing. All we need is a large enough green sheet, a support surface, and a bright enough lamp to illuminate the set. In this manner, we have all of the elements that would be found in a full-size set. A series of markers must be drawn, just as they would for match moving on a traditional video. In the case of a green screen set, we don't have any ready-to-use markers, so we have to add them manually. Simple adhesive labels can be cut into many small squares and easily adhered to the green sheet. When making and placing the markers, keep simple shapes in mind, such as squares or circles. The markers should be neither too large nor too small. There is no specific rule to follow in this case. The important thing is that the markers are clearly visible and not too small when viewed from the camera display. We now arrange the markers so that they cover the entire surface, including the table and the background. It is not necessary to use a large number of markers. A dozen or so will suffice. Remember that the markers will be manually removed from the final compositing. Using a strictly necessary number is thus unquestionably a good rule. Remember to take note of the following information before taking the final shot. The focal length that has been set on the camera. The altitude from which we are shooting. Finally, the distance between two markers. These data are important because they will allow us to make more accurate match moves. We can now go ahead and take our shot. To practice, let's start with a shot with no objects in the set, just the green paper and the markers. Obviously, in real life, we will have positioned a subject. The video can now be imported into the camera tracking software. I'm using PF Track here, but the same concepts apply to any other program, including Blender. First, it's useful to specify an information about our camera that we don't generally know, namely the size of its sensor. We can set this value in the imported video's property. If we don't know, we can consult the manual of our camera. At this point, we can start the manual tracking by selecting the markers that we have added to the green paper. Once we've tracked all of the points, we'll be able to reconstruct the camera's movement. Before we do this, we can make the camera solving more accurate if we also add some information about the camera we used to take the shot. For example, we marked the focal length used so that we could enter this information as well. In relation to the lens distortion, we can let the software handle it automatically. All that remains is to begin the solving, to obtain the camera and marker's spatial data. Finally, remember to correctly define the scene's coordinate system. The tracking data can be imported into our preferred compositing or 3D software. In this example, I imported the data into After Effects. Following the import, we find the markers that were used to generate the virtual camera. Looking at the camera properties, we can see that the focal length and sensor size data match those obtained from the camera tracking software. It is always important to double-check the coincidence of these data, because it is possible for these data to be different when passing from one software to another. In this case, manual correction is required. Otherwise, the camera tracking will be incorrect. The markers in the compositing software are used to correctly place 3D objects in the scene. Let's try adding some objects to see if they match the real scene perfectly. In these cases, it is critical to ensure that the objects are perfectly anchored to the ground, using one of the markers as a reference. If we notice a displacement of the 3D object with respect to the marker, this indicates that there is a problem with the virtual camera calculation, or in how the scene was recreated in the compositing or 3D software. Let's try inserting other objects, not just inside the green sheet, but also on the table. Another realism feature is the addition of shadows to the 3D objects we've placed. To get shadows, we need to add a three-dimensional plane at the same level as the markers on the table. Adding a simple plane, however, is not enough. It would be opaque, obscuring the underlying video. To solve the problem, we need to make the plane transparent, but only visible to shadows. But let us return to our original goal, which was to create a compositing between a subject shot on a green background and a virtual scene. Let's start over with another shot, this time with a subject in the frame. Let's move through the various stages of the match. I'm going to re-import the data into the compositing software. This time, we add some objects and play the movie to ensure that the result is correct. Before making the green background transparent, let's try to unify the real shot with the virtual world. The lights are the first element on which to act. We must, in fact, adjust the light of the virtual set to be as close to that of the original set as possible. The best way to do this is to use the shadows as a guide. We have to adjust the light's position so that the shadows cast by the objects match the real shadows. We must also adjust the softness and contrast of the shadows to make them as close to real shadows as possible. After we've adjusted the virtual light, we need to match the colors of the live footage with the virtual scene. This step, along with adjusting the light, is critical in giving the final compositing a natural look. The coloring of the scene is influenced by a variety of factors, including the hue of the light used to illuminate the set, the reflection of the light in the surrounding environment, the camera's color balance, and so on. When we add 3D objects to our scene, their color is determined solely by their materials. This means they don't receive any color from the light of the live footage. To make the compositing believable, we need to add a color tint that is similar to the one in the real video. There are several ways to accomplish this. One is based on adding color references to the original scene. For example, we can include white and gray cards. Or, even better, a color checker, which is essentially a palette containing various standard color references. Using the original photograph of the real set and these color references, we can return to the compositing software and even out the hues. When we examine the color checkers black, gray, and white areas, we can see that they are never completely neutral. We always have a more or less pronounced hue. In this case, for example, we can see that blue has a noticeable predominance. Now we need to color correct the 3D scene to equalize the dominant colors in the neutral areas. We can, for example, add a neutral colored object and use color correction to introduce the same dominant colors in the movie. When we examine the hue of the white-gray tones in the 3D object, we find that they are perfectly neutral. As a result, we can use the RGB channels to create a chromatic dominant, similar to the one seen in the live footage. Let's return to the topic of shadows for a moment. We previously adjusted the light to add some shadows similar to those seen in the video. These shadows are cast on the newly added virtual plane. However, we have a problem, that is, how to cast shadows from a virtual object to a real one. Assume, for example, that this object is placed in front of the lighthouse. We expect a shadow to be cast on it. In reality, the only shadow that exists is the one cast on the virtual ground. Obviously, this occurs because the lighthouse is not a real 3D object, but rather a component of the video. As a result, we must repeat the process used to create the shadows on the floor. Basically, we need to add a 3D object that has the same shape as the object on which we want to cast shadows. First and foremost, ensure that it is properly positioned. We must now make it invisible, so that it only receives shadows. The bottle now appears to be casting real shadows on the lighthouse, but it is actually casting shadows on the hidden object we created. These objects, which serve only to receive shadows, are called matte shadows. We have another problem, which is the opposite of what we saw earlier. That is how to cast shadows from a real object on a virtual one. For example, the shadow of this object, the lighthouse, on a virtual one, the paint pot. The trick is to always rely on the invisible object that we have created. This time, I'm also including the ability to cast shadows. Finally, we can begin keying our green screen set in order to isolate the subject. Of course, we must also remove the tracking markers. The floor can now be set as a visible object. All that's left now is to complete the 3D scene as we wish. The basic concepts are what we have seen so far. Finally, let's see how to make the lighting even more similar to the one in the real video. We've already seen how to place the lights to create similar shadows. We also learned how to change the colors of the virtual scene. However, we can go a step further and ensure that the virtual scene is lit by the same light as in the real video. This is known as global illumination. Essentially, we have to make an HDR image of the set. This image is then used to light up the virtual environment. The lights in the image are used as true light sources. The set must then be photographed in 360 degrees and saved in 32-bit HDR format. Now, as before, let's add the 3D object to see how the shadows are cast. The HDR image is imported into the 3D software and used as a global illumination map. we have to rotate the image to match the position of the lights in the live video. Each pixel in the HDR image is transformed into a light source. This means having the same lighting as in the video, as well as the same coloring in each area. So, the virtual objects are lighted in the same way as the real ones, and this is the final step in video compositing between real and virtual objects.